Alrighty, we are alive, and today this session will be presented by the one and only David Fowler. That's one of the best-known .NET architects at Microsoft, creator of SignalR, and he did a lot for ASP.NET Core. He has been at Microsoft for 13 years, working on many stuff, but mostly in .NET space. And he created several popular OS frameworks. Yeah, I think that I could spend a lot of more time describing all that he did for .NET. But anyway, without further ado, David, the scene is yours.
Awesome. Thanks. All right, so this talk is called Implementation Details Matter. And the talk is mainly to get you curious about learning more about what you're using. So I'm David Fowler. I've been an architect on .NET for about a couple of years now. Been working on .NET and dev tools for 13 years. I co-created NuGet, SignalR, ASP.NET Core, and Azure Signal Service, and I worked on a bunch of other things as well. I also spent a bunch of my time helping what we call first-party customers in Microsoft, helping them diagnose complex problems when they're in production. As people adopt ASP.NET Core and they're running it in the cloud and they're running it at scale, as you can imagine, a bunch of services inside of Microsoft and outside of Microsoft are running, big services at scale on .NET Core. I get to learn about their problems and learn how to help them. And as I see more patterns, I kind of want to have this talk to kind of help people understand how to think about the problems, how to think about the space, how to go about learning about what you're using. And then if I have time left over from meetings, I can write some code every now and then. So .NET has been around for like I think 20 years next year. So it's been on for a long time, more than half my life, and it has evolved a lot. It went from kind of being like a desktop first, a client story to supporting kind of all things like WCF and all that stack, and it's been evolving into a high performance modern I want to say cloud platform because I work on the server. But essentially, we want to help people understand that .NET isn't what it used to be, and there's this thing that I've been calling modern .NET. So we want to help re-educate people that kind of knew .NET from the elder years, and to kind of rethink about how they write scalable .NET applications. I spend a lot of my time helping people diagnose problems, helping people design libraries for high performance, because it really has to be not just .NET itself, but the entire ecosystem of libraries that are using .NET. They have to kind of rethink how they think about the entire model. There's span, there's all these new types now to do things, and the team has been very much in a performance culture now. I think since Tech Empower, since doing ASP.NET Core, since doing that stuff, the team has a culture of performance, and there's a lot of FUD around like don't optimize things before you need to. And I think we've kind of found the balance. At first, I'd say .NET in the beginnings, we didn't really think about performance as much, and then we thought about it too much at one point, and now we're kind of in the middle where we optimize things that we think are going to be used in hot paths. So I want to kind of kill the FUD around premature optimization. So details matter because humans build software and humans make assumptions. It's not always that they're trying to optimize for their own themselves, but whenever we design anything, a library, a subsystem, some kind of software, there are some assumptions in mind about where it's going to be used, how often it's going to be called, and those things. Some things are very hard to express in the type system. Like I couldn't express that this thing should only be called once per request, right? That's not a thing I can express. So a lot of the things that can't be expressed in the code have to be expressed in documentation, or you kind of have to read the source code to understand how it works, right? And those assumptions make a big difference at scale. It may not matter if you only call this function 5 times in your application lifetime, but if you're calling it 5,000 times, like maybe it makes a difference, right? So understanding those details help you take advantage of the subsystem. If you understand how the GC works, you can use it better. If you understand how the thread pool works, you may be able to use it better. Also, those details help you root cause issues as well. So if you're in a bind or things aren't working well, it may help you if you understood how the system worked, so you can kind of pinpoint where you should look next, right? So some examples of those assumptions are, software engineer would say something like, there should only be a handful of these in practice. This should only happen once at startup. Have you ever had a time where you were debugging something that was only supposed to happen once and you saw the breakpoint get hit like 10 times? It's that assumption that's like, okay, that isn't supposed to happen. And if that happens, then that means the whole software is unstable because we expect this cache to only be to be populated by the time the app starts. So it shouldn't happen more than once. No one is going to create this per request, right? We saw cases where someone created something super expensive per request by mistake, and they're like, oh, I thought this thing was going to just parse JSON, and it's like, no, it's doing these 10 other things and causing leaks, right? So understanding that software is built by humans and humans make assumptions and mistakes, and you have to be aware of that when you use the software, because a lot of those things aren't kind of described in the actual thing being built. They're just assumed, and you have to kind of learn that stuff the hard way. So what does at scale mean? At scale can mean a lot of different things. It could mean number of users. It could mean the size of the data. It could mean the number of times the data is being processed. So it could be, I was handling 10 requests per second, and then I got Hacker News. I'm on the front page, and now I'm handling 10,000 requests per second. And the characteristics of your application change at that point. Like maybe the thing you were doing that was very cheap, where you weren't caching anything, now needs to be cached, right? We always see news stories about things going down because there wasn't a cache, because the load went up, right? The same thing happens here, where the app was working fine for a long time, for like, I don't know, 5 years, and then all of a sudden you got front page on something, and now you're like, your app has to scale a lot more. And the app wasn't designed for that scale, so you have to go figure out how to reevaluate what you did before to learn to make it scale. And then scaling as an engineer means you really have to figure out how much to learn and how much to ignore, right? You don't want to have to look at the assembly for every single library you're using. Like I don't go looking at the assembly that the JIT creates for every function code I use. But where it matters, you go as deep as you need to. And that takes time and experience. So don't feel bad if you don't know where to stop, where to look. The more you do it, the better you get at kind of going broad, going deep, and then cutting off at some point, so you don't end up like burning cycles, trying to micro optimize things that may not matter. All right, so how much do you need to know? You should be curious about what you're working on. I know a lot of the times I hear things about, we just need to get this working. I think that's completely fine. And there is a point of a point where you need to stop digging too deeply, but you should always be curious, and you should always have a general sense of how your subsystems work. So if you're using link a lot, you should understand how it works, so you don't go doing something n squared for a large input size, right? So building up a mental model for how the area works is a very effective way to kind of like not have to dig in deep to everything, but you have a very general sense of, here's kind of how link works, here's how group by works, here's how whatever function you're calling works, right? Like the Cliff Notes. I'm not sure if this is a global term or phrase, but Cliff Notes, when I was doing English Lit in secondary school, you would read a book and you would understand the whole book and every chapter, and it would be long to read, and then you could read the Cliff Notes, and the Cliff Notes gave you a summary, like an overview of what you had to know about each chapter. Do that with code. Like read the code for fun, go enjoy like learning about the actual code base, because you can learn techniques that way. But if you're trying to get something done or trying to get a mental model about the area, you just need the Cliff Note. You need to understand how this area works, how this type works, how this function works in a general sense, right? Not every detail. Too long, didn't read, right? So how do you learn details? Build lots of things. That's kind of generic. Read code that others wrote is a very good one that I spend my time doing. So there's a lot of open source code. Dotnet itself is open source. You can read the source code. Now I spend a lot of time reading things that we call into, just to learn how it works. It's just to understand what the connections are, what it calls into. Talk to subject matter experts. We have a lot of forums now for .NET where the team and a lot of experts to hang out to kind of like help others and talk about stuff. Like Stack Overflow is interesting. Like I scratched out the answers just because some answers are are just old and wrong. But Stack Overflow also works if you want to ask questions. But you can actually talk to the team and talk to experts on GitHub or on Discord or on a lot of different forums. Reading documentation, including the fine print, is a really good one. Documentation, our documentation is, I want to say, good and bad in different areas. A lot of our documentation has the remark section and has a lot of fine print about how to use APIs. If you do have time, read the fine print, read that extra remarks to figure out, what are the quirks of this API. And we ourselves have to do more of that stuff too. And then when you're done, when you're finished these things, read the source code again, right? You'll find a lot of gold there. I think a lot of the engineers on the teams themselves like jump around source.net, which is a thing that we built internally to kind of like browse source that's linked together, just to learn how the things that we call ourselves work in .NET. So it's super useful. So is this just all this preview just for a performance talk? Am I budgeting it for performance talk? Yeah, sort of, right? That preamble was just to get you warm to the fact that you should be curious about what you use. You should care about what you're using. You should care about the functions you're calling. You don't have to go too deep, so don't feel bad about not knowing stuff. Everyone's learning, right? We're on this journey. So here are some examples of the assumptions we make in .NET about how, well, assumptions about the subsystems in .NET. So the GC will optimize for your application's throughput. If you're trying to figure out what the GC isn't collecting, it's probably because it didn't see a reason to, right? It's trying to basically not take away your CPU time by collecting garbage. So it's trading off CPU for memory for CPU, right? So I've seen a lot of issues where people have filed bugs saying the GC that doesn't work, it doesn't collect on time. And I'm like, yeah, I get why you're saying that, but the GC is optimized for this very specific use case, and it's why it has all these knobs, so you can kind of tell it, hey, I care about memory, not performance. I care about this much performance. I care about, don't collect until you round up of all the memory it has, right? That's why we have server GC and client GC, and they work differently, and they have different modes. So just understanding that at a very high level can give you big clues as to why things aren't behaving the way you think they should behave with the GC. Timers is a very interesting one. Timers are optimized for creation and deletion. So the assumption is that they don't fire most of the time. If you think about creating a cancellation token with a timeout, that will create a timer entry. And the assumption is you create a cancellation token per request, and you pass it to an API, and then you call dispose, and it never fires. And that's the case the timer queue is super optimized for. So we chose a structure under the covers that lets us add and remove things very quickly. So it's optimized. It's a doubly linked list optimized for creation and deletion. If you look at other platforms, their timer queues are a heap, and they're optimizing for timers firing, so they can find the thing due very quickly, right, in O of one time. Where as for us, we have to actually do an O of n operation to find timers to fire, because we optimize assuming that they won't fire most of the time. That, just knowing that, could kind of help you sense or see when things are going wrong. We had this team, they asked us, they had a perf issue, and they were looking at counters, and they had 400,000 timers, and we were like, that's probably an issue, right? You aren't supposed to have that many timers, and I think most of them were periodic, so they were firing every now and then, and that just isn't a thing that we see super often, right? And it wasn't that it was a bad thing per se, but the timer queue was not optimized for that use case. So every now and then you hit a scenario where, we didn't anticipate this scenario, this use case to happen. So, you can't use this thing. You might need a special thing for that. And then configuration, we generally believe configuration is built once at app start, but it changes behind the scenes as your config source changes, right? We had this team use the JSON configuration source as a JSON parser, and they were creating a configuration source once per request and building it, and they weren't disposing it. So it kept adding file watchers to the same directory over and over and over, and it killed the entire process at some point. It's another example of a thing that is really hard to kind of express in the type system and the API. You kind of just have to know that this thing, and I guess you could say, if it's disposable, dispose it. But a lot of people don't read the fine print, and config looks pretty harmless because it's just like the APIs don't really scream you have to dispose me. But that was a case where we just had to tell the customer, hey, don't create a config once per request. That's not the use case we envisioned, right? So what I did for this talk, I grabbed a bunch of code from Microsoft because I'm pointing fingers at ourselves, not other people, right? Yet, at least. So they're real examples. I have removed any trace of any Microsoft specificness. It is a very generic example that we're going to look at. And we'll look at the problems and the root causes. And these code samples are in the hot path. That part is super important. So these examples came from teams who were running in production, looking at running services. They had problems. They ran a profiler. They found that these were in the hot path. And we solved the problems after finding these because they ran it in production, right? If they weren't in the hot path, it's not to say that they aren't important to optimize. It's just that maybe you wouldn't spend all your cycles trying to optimize everything if it wasn't that important, right? So that's important. And this is just a joke from if you've ever seen Law and Order. I've changed it. We changed the names to protect the innocent teams and innocent developers who wrote this code. There's no shame in having your code be inefficient. We're all trying to learn this stuff, so don't feel bad if you have the same code in your applications. All right. So let's talk about the code now. Hold on. Is that JavaScript? Hold on. There you go. All right. So here's a simple function. I'll let you read it for about 2, 3. I don't know how long. A bit. Give it a stare. And if you have this code in your applications, like don't go changing it. Just read the code. It's very simple. It's a function that takes in a byte array, will decompress the entire byte stream and return a byte array of decompressed bytes. Right. So it looks like typical .NET code that you would use. So to decompress bytes in .NET is a type called gzip stream. I'm passing it the decompress flag. I'm passing it the byte array wrapped in a memory stream. So let's take a look and see what this is doing. So I grabbed the input buffer. It's a raw byte array of data. One of the things I want to say here as well, like there's no way to express in .NET or in any language that I've seen at least that like this byte array shouldn't be like massive. It's not. Imagine if this was 2 gigs, right? You really shouldn't be passing the 2 gig byte array like of contiguous memory to this function. But there's no way to express that. So engineers basically use the API shape for what it is, and they will pass in a memory stream that has a single byte array that is 2 gigs, right? And maybe it's fine if you have that much memory on your machines, but then you run it in a container that's constrained, and then it all blows up, right? So I pass in a byte array. gzip stream will internally allocate an 8K buffer, right? That's not even shown here. That you would only see that if you run an allocation profiler. It'll allocate 8K buffers to, because it wants to give zlib, the library we use internally to do the actual compression. It wants to give it big chunks of data. So you make a new gzip stream and it allocates an 8K buffer. And then you make a 4K buffer, and 4K is good because that's the size everyone uses to copy stuff, I guess, by default, right? It could be bigger, but whatever. And then you allocate a memory stream, which is essentially a list of byte, right? It's an expandable byte array. So far we have the input buffer that was allocated because it's a single, it was passed in from the caller. And then we have a gzip stream that allocates 8K buffer. We have the 4K buffer that I allocated to copy the bytes from the gzip stream into the memory stream as an in-transit buffer. And then we copy the data, we read the data from the gzip stream, and then we write it into the memory stream. So we get the overall set of decompressed bytes. And we loop while we have data left in the gzip stream. And then we do toArray. toArray will take the internal buffer in memory stream, will create one of the correct size based on the number of bytes that were written, and will return that. Does anyone see a problem with this? Does anyone see like how many allocations there are that are some that are very obvious and some that are very hidden, right? And don't get me wrong, the GC is amazing. The GC works really well, but there's a lot of things here that can be changed to be more efficient. So let's talk about some of the problems or some of the issues. And this is the source code for deflate stream, which is the base of gzip stream. You can see it has an 8K block hard coded. Now that 8K before .NET 3.1 was not pooled. Actually was allocating an 8K byte array every single time you allocated a gzip stream. And actually in ASP.NET Core, we found this when we were trying to write the compression middleware, and we were trying to like make it more efficient. And then we saw this allocation that we couldn't get rid of, and it was like, oh man, this 8K is killing us. It's pooled now, which is better. So it's not a fresh 8K allocation every time. But if you have a lot of concurrent operations going on, you can still end up having a lot of the 8K buffer kind of hard coded in the streams for the whole time. See that buffer? I can't point. You see that buffer field there? That holds the actual buffer used. All right, so what's wrong with this pattern? Nothing is wrong, but it does allocate a lot. And in server applications, I find this pattern to be very common, where people kind of take large streams and they do to array just to get it into a byte array, because the APIs you're calling may take a byte array. Like maybe you don't have a choice. Maybe you need to have a contiguous piece of memory to pass data into. In that case, you're kind of screwed. You don't really have a choice but to create a byte array to pass data to that API. But if you can avoid it, like you should. Large temporary buffers that are throwaway per operation are really bad. It wreaks havoc on the GC. It can thrash your large object heap. You don't want that. It can cause excessive Gen 2s. You want to be mindful about buffer copies and allocations. Buffer copies tend to show up as high CPU. And allocations will show up as, well, the GC you will end up having the GC run a lot more than you need to if you have this pattern in your application. Use streams or pipelines for large data sets. And if you need to use in-memory data, if you need contiguous memory, do reuse the buffers that were used. Don't just do a memory stream to array. In fact, I would almost say to array for memory stream is almost harmful, somewhat for large scale applications. There's a type that Microsoft wrote, and I think it came from the Bing team, called what's it called? It basically it will manage a bunch of streams for you that are large. It's called I can't remember the name though. Memory Stream Manager, something like that. And this is the fix. The fix sometimes requires the caller to change their pattern. So yeah, like this is cheating because I basically changed the result to be a stream, but you want to force the caller to copy data into memory if it needs that. But you don't want to do it here. If you do need it to be part of a single memory stream, then you want to use pooled buffers to do so. Right? Don't use the actual byte array itself. Actually, it would be ideal if more APIs took spans, because then even if you use a memory stream to copy the decompressed bytes into, you can actually get the internal buffer from the stream. So you can actually get the internal buffer from the memory stream, and then you use that passed in as a span to other APIs, right? The buffer in the memory stream is oversized because it doesn't know how much you plan to write in the future. So it has to allocate kind of like a bigger buffer, and it doubles in size every time. Yep. All right. Yep. So sometimes when you want to optimize, it means changing the pattern completely. All right. This is one of my favorites. This was found in .NET Framework, and I won't say where it was found, but it was found in .NET Framework. And it was trying to optimize the string. So I guess that meant it was trying to intern whatever the input value was. It's funny. When this was found, it was found in some high performance issue in Microsoft, and then someone found it, pinpointed it, and then it turned out it was doing something prematurely. It wasn't required at all. But how does string interning work? Like, what does isIntern even do? It doesn't return a bool. So it returns the intern string if it was interned. Otherwise, it doesn't return the string at all. And so one thing about this pattern that I want to mention is sometimes when you use things built into the framework, you think it's magic. There's runtime magic. The JIT is super smart. The team that builds the actual applications are super smart. Remember, we are smart, but we're all humans, right? We all build things in similar ways. You want to think from first principles as to how does this have to be implemented, right? Like, what is the most obvious way to kind of to cache a string literal and store it for a long time, right? Based on the actual, based on the string that was passed in, I want to cache that string instance, right? So it turns out there is a dictionary, and it happens to be in C++, but it is a dictionary. Think of it as a dictionary of string to string, right? And it takes a global lock. Like it's kind of terrible, but it's kind of how it has to work, right? So it takes a global lock on the map. And then this is the dictionary that is used to store the actual intern strings. And it has a to-do here saying that we should have a more efficient version, which we should probably implement at some point, I guess. But right now, it takes a global lock if you are looking for a string that isn't in the intern map. So this was causing a ton of contention, and there wasn't actually an easy workaround for this team. But it turns out the code didn't need to intern strings at all. If the string is already intern, then it does actually a lock-free check in the map, so you don't have to take the global lock. If the string isn't intern, you pay that cost of a global lock that is actually deep in the runtime, and it's really hard to work around. So if you need to intern strings, you should probably use your own cache or use a package that does it on NuGet. There's one called Ben.dot, I think, string intern that does this more efficiently. I know the runtime should probably fix that issue, but I'm guessing it hasn't been fixed for a long time because string interning isn't really I shouldn't guess that, isn't a super used feature in high performance code because maybe they found this bug or feature. Oh, my favorite, link. This third code sample was trying to do a breadth first search on this operation tree. And so I have a list of visited operations and a hash set to keep track of what I've seen so far. While loop, we'll loop over all the operations that I haven't seen yet. We'll dequeue it, do a contain check on the ID, out if I've seen it already, and then the super cool one-liner at the bottom that is very classic link. Current operation, child actions, where is complete, to list for each in queue, right? That's a beautiful line of code. But it hurts my eyes because of reasons. So here's the link that does any. Any is fine, it's a link. Here's the where clause. Then we allocate a list because we want to call the for each function. So it's funny, I've seen this pattern super often, and it's always to use the for each function because it's only on, I think, list of t. So you have to like materialize the enumerable. You can't just loop over it. You have to actually do a to-list to get the for each function that then you have to use to do the enqueue, right? And this looks super tight and small, but passing the method group here actually forces a delegate allocation every single time you're looping. And the fix here is like, hold on, super simple. Hold on. Yeah, sorry. So instead of using any, use the count. The count is much easier to understand, and it's very simple, and it just does a quick check on the actual size of the list. Any is very optimized, but depending on the kind of collection being used, it may not be that optimal. It may have to allocate per call to any. And then you can just do an add on the hash map. It returns a bool. The hash set it returns a bool telling you if the operation finished successfully or not. And then instead of doing the super fancy for each in the function, you can just do it as a normal for each function, the for each statement that doesn't allocate anything at all, and that checks if item is complete and then enqueues the operation. So there's no delegate allocation, there's no link, there's no list allocation happening. It's very simple code, straightforward code. I know we all wish link could kind of unroll to do this, but as of right now, link is extremely optimized, but it doesn't do these kind of optimizations, right? It isn't at this level as yet. So link to objects is super powerful and expressive. And you should definitely use it in your code. It's very nice to use, but you shouldn't use it in hot paths, right? Hot paths are the key point here. Do not use link in hot paths, right? In the framework, we tend to not use link a lot of places because we're trying to reduce startup as well. So we may even go as far as to remove link from our startup path because we're trying to make that super fast. But in general, you can use link just fine. But if it's in the hot path, it's an easy target for things to kind of remove from the code base. This is a very simple one where someone was trying to parse, I assume, a UTF-8 JSON byte array DOM string. Does anyone see the issue with this? I can't see your comments, but I'll give you a second to look. So it calls get string on the actual DOM string, then calls toChar array. It's char, not car, by the way. And then calls parse on that string, passing in the index 0. Yeah, the string here, so we get a string, we get this single contiguous string in memory, and it's thrown completely away, right? Completely useless. So instead, you can call get chars, get the char array from there, and then parse that. Now, this isn't the most efficient you could do. You could actually, there's an overload of get chars that takes in the actual char array you want to use to fill in. This still allocates a char array that could be huge, right? You could end up on a large object heap still. Instead, you can actually, if you know how big, or if you have a pool of buffers, you can actually rent from that pool and call get chars passing in the buffer itself, and then use that to parse the actual JSON payload. But in this case, I believe the JSON strings were smallish, but also that can't be described anywhere besides a dot comment, right? You would need to have a comment saying, we expect JSON DOM string to be under 85K. Otherwise, it's not a good thing. Because maybe the thing being passed in is a pooled byte array, but then you immediately go turn around and turn it into an allocation, which is kind of unfortunate, right? You kind of want to preserve that high performance nature if you're trying to build that kind of API. This one hurt my soul a little bit. Give it a read. So we want to check if the file path is valid, and we're passing in a path, and then we do regular expressions, which is my arch nemesis. But it's much faster though, and it's going to be even faster in .NET 6, so maybe I won't hit it anymore. And then we pass in compiled and ignore case. We match, we try to lower a bunch of paths, and then we do comparisons on the potential ID of the file system. I'm not even sure where I copied this from. It was just somewhere internally. All right, so I don't know where this is used, but it was used in a hot path. And one of the issues is this code is probably fine, or we wouldn't have found an issue with this code if it was just being called once at app start, but it was being called, like, I believe it was per request. And we're compiling this regular expression per request. To lower calls, yeah, trying to do a case-sensitive comparison. So compile regex basically compiles this state machine, right? So typically when you don't compile a regex, we build this state machine, a DFA or an NFA, based on the expression, and it's very optimized, more optimized in .NET 5 and 6, I believe. And it basically gives you a machine or a function you can use to kind of match an input string, and it will tell you if there was a match or not, and it may capture things, and there's a whole theory behind how you build an engine for this stuff, right? We can further compile that intermediate format into IL that actually runs a bunch of code to do the same matching, and it's much more efficient. This isn't cached, so you're supposed to use compiled. You're supposed to use this feature and cache it yourself. But in this case, it was being called, once per request. So it basically ended up creating this giant set of IL per call, which is really bad, right? You really want to cache these calls aggressively. So the fix was pretty simple. Move this outside of the actual function call itself, and then some other things to optimize, like parse the ID before doing the comparison. And then instead of calling toLower, which will allocate, lowercase strings for the paths that were passed in, just do a case-insensitive comparison by using or don't ignore case. Right. This one, so I gave this talk earlier this year at a group, I think in the UK, and this particular one I think caused a bunch of drama that I didn't mean to cause. So here's a log level enum, right? So I'm trying to convert this log level enum into a string, right? So I do enum.toString, and I get the textual representation of that enum field. Seems pretty simple, looks straightforward, works just fine. How does enum.toString work? I actually had no clue until I looked, right? I had some ideas of how it could work, but I didn't actually know until I looked. And it essentially calls into the runtime to get the values of the enum, like all the values, and enums can have numbers, so you can label your enums like 10, 20, 40, 80, but by default they go from 0 to n, right? N being the number of fields you have in the enum. And it does a binary search trying to find the value, which is pretty efficient. And this is actually much better than what it did on .NET Framework, so it's much faster. But that seemed like a lot for a very simple enum. So the way to optimize this, right? It caches the enum information from the runtime, and then it does a binary search to find the right enum index to get the value, and then it gets the name from from the values index. So there's two arrays, an array of names and an array of values, and it keeps those and caches it per enum. So you're paying this added cost of memory because the runtime has to kind of like grab that information and cache it per enum, but it's cache launch per process, so it's not a huge problem. But this is actually much more efficient. It's much more efficient because there's no runtime lookup. There's just returning string constants based on this switch statement. Now, if these enums were not going from 0 to n, the compiler could generate potentially less efficient code for that. But in this case, it actually works super well. And this should probably actually use name of instead of using the actual string constant, but it's fine. No allocations, no toString allocations. It's using cache strings. These are all like in the actual binary as like in the section that has for data. It's constants, right? There's no allocation here on the GC heap. And then scan for so here's another code sample that is pretty interesting. This came from our memory cache. It was a bug that we had up until .NET 5 or 6, I believe. It was the background thread that was trying to scan for expired cache entries. And entries is a concurrent dictionary. And it's using is scanning through all the values, the cache entries were values. And it checked to see if they were expired. And if it was, it would remove it from the cache entry. Pretty simple code. So does anyone know how .values works in concurrent dictionary, like what it does under the covers? So it's funny. I actually had a tweet about dictionaries and different scenarios where you'd want to use them. Then there's the fine print on like, okay, you want to use concurrent dictionary. You heard it's good for concurrent scenarios. It's fine, right? It's reads are lock free, writes are not lock free. But there are other APIs on the type that basically lock and take a snapshot of the entire collection. .keys, .values. There are also a bunch more that do the same thing. So you kind of have to read the fine print on the API, right? So this is the part that gets tricky. You've read the API summary. You've chosen to use it. It was the right choice, but then it has these other details that aren't immediately obvious to you, right? By default, the number of concurrent writes is equal to the number of cores. You have that's not super important for this scenario. But what was happening here was every time we scan for expiration, it would copy all the cache entries. It would lock on the collection, copy all the cache entries, and then like, do work, right? And that was kind of what we we're trying to avoid in the first place. So the trick is to loop over the actual entry list. Do not loop over values or keys. it's weird because it seems like a trap, but in some scenarios, you actually do want a snapshot of the dictionary at that point in time. But if you're trying to basically enumerate over the dictionary values, just enumerate over the entries, and it doesn't snapshot, doesn't copy, doesn't even lock, all right? And then this just works, and it's much more efficient. This one actually caught a couple of our customers for large-scale services. I think it was a bug a long time ago somewhere in AutoMapper, where it was doing something with dot values or dot keys, and that was a big issue in itself because it wasn't being. There's no way to know how a library is going to be used, but in this specific case, it was being used several times per request, and it kind of killed the whole service because of this issue. And it only was an issue when the entries collection got to a certain size. So that's the issue with skill. Like it works fine for the first, I don't know, half year, and then you get more skill, and then the whole thing falls over, and you have to rethink your whole design. So lessons we learned from this: measure what you care about. Do not trust your intuition. I trust my intuition, but don't trust it. Trust a profiler. Think about how things are implemented. I think this is a big one. Thinking about things from first principles gives you more perspective on how it kind of has to work, right? Like how does this thing work? It does feel like magic, and you don't have to understand all the layers all the time. But for things you're calling directly, you want to kind of think, how does this work? How does it have to work? And just because the thing is quick to call and easy to use, like LINQ, doesn't mean it's fast to execute, right? You may be very productive, and you may have gotten the whole thing working pretty quickly, but it might be super slow, which might be fine, right? It's all trade-offs. You need to figure out where to care, what to care about, and using tools like profilers can actually help you figure out where to look, right? You don't want to go saying, let me go fix every single string allocation in my entire application today, but you should. But you want to use the tools to help you figure stuff out. This is a good one. The compiler isn't nearly as smart as you think. I think Jared just went on before me. The compiler is really good, but I think sometimes people see how good it is and they kind of think it's magic, and it's not magic. It's code written by engineers like me and you, right? Yeah. So don't just assume that the compiler will turn my my toString enum. Where is that code? I went too far. Don't assume that the compiler will take this and turn it into the switch, right? Like it doesn't do that. Maybe in theory it could, but right now it doesn't do that, right? And then tools to use for research. I use source.net a lot to find the source code for .NET, to look at how things are implemented, to look at what features are being used, to look at how things are done in different places. It's a super cool tool that's used by the team to kind of to find source code and look at things. Sharplab.io I use a lot to figure out how code is being compiled or edited at the lowest layers. Yeah, it's a fun tool to learn how the code you write gets transformed into the various phases. The most fun one is to translate C# into C#, because C# will lower your code into different IL, and seeing how that decompiles back into C# is kind of fun. Like for example, for each over an array will turn into a for loop, right? Grep.app is also pretty cool for finding coding patterns on GitHub as a whole. Decompilers like ILSpy or any decompiler. Asking questions on GitHub issues is fine. We're fine with that. We answer questions all the time, and so do other enthusiastic contributors. C# Discord is pretty good. I didn't put a link in here, but there's a Discord channel for C# that has a lot of experts available to learn things from, ask more questions. This code isn't bad. Everyone's learning. I wrote code like this, probably in the last, I don't know, year or two or so. No one's perfect. These examples came from Microsoft, and the key there was just showing you that even at big companies, this problem exists, right? Like people are still trying to learn how to write efficient .NET, and we're trying to help educate more to kind of learn how to do more stuff like this. And I actually learned a lot of stuff from making these slides. It's having to research how each of those calls were working. Was a lot of fun. I learned stuff from just doing that. Okay, here's the last piece. Details are volatile, so things are always evolving. Make sure you're up to date. I've seen a lot of patterns where people came from .NET Framework assuming they knew how things worked when we have totally gutted the implementation in core. So you want to make sure you have an up-to-date recollection of how the subsystems that you know work. Details can change, but concepts don't often change. We don't often introduce whole new GC modes, even though we probably are pretty soon. And when they do, you learn those things. So focus on concepts, not details, for the most part. And then you need to keep measuring. It's really hard to, if you're doing a performance push and you measure once and you stop measuring, you may be in trouble, right? You need to keep measuring as things change over time, so you understand how changes you make or anyone else makes can regress or change those measurements. And then the recipe that I've been trying to use is building a mental model for the big parts of your system. Then you want to figure out which parts actually need to scale, like which parts are your hot path, like what things are running per request or on big parts of data, big sets of data, etc. And you want to zoom in on those things first. Don't go trying to optimize things that don't matter. You want to spend time working on those details, right? The parts that matter the most. And then optimize your code appropriately using different techniques. I think I've shown a few here. And that should just be enough to get you interested in this in the first place, right? And now I will take questions.
Awesome. And we have some. So we'll start first with the comment that we were discussing in the background before. Thank you for the mention. I think we didn't manage to make it happen for the second time.
If they would use more C#, then maybe you would. I'm kidding.
All righty. Okay. The second one is related to your async task best practices guidelines. And are you considering something about TPL and channels?
Yeah. Okay. That's funny. I need to figure out how to scale those. The async guide came out of pure frustration with having to answer the same questions over and over for different people. And I was just like, let me just write this in one place and just try to be more black and white, because typically the guidance we give is very much, depending on the situation, you may want to use A, B, or C. And it's kind of like, let me just be very like specific here. Don't use .wait, don't use .result unless you know what you're doing.
Okay.
Yeah, I plan to expand to do HTTP client as well, because that one is a pretty hot topic. Yeah.
Alrighty. That was a mention when
that's
you
what
were discussing.
Recycle and restream. Yeah, that's what it was. Yeah. The Bing team built this and they use it, and it is super efficient. It's good. Good stuff.
Cool. There was a question about links to the snippets you shared.
No. Yeah, so I don't have any links to the snippets. I could probably make the slides available, and that could be a way to do that. But the code itself is like, it's basically mangled from internal code turned into like something generic as an example.
Okay. Yeah. So if you send us the slides, we can put them at the bottom as a comment or in a description. There was something about others people's productivity.
Yeah, this is a good one. It's tricky. So the reason I work on Dotnet is because I like being able to influence make people more productive, right? And fix really hard things that make developers' lives like work much better. Writing code myself is a lot of fun as well. So I have to balance like how much time I spend doing each thing. But I think I found a good balance. I write code when I want to, and I spend time helping others when I need to. I would say you do get the force multiplier effect when you can kind of affect the core part of a team that kind of bubbles up to a big part of a bigger team. So I tend to work with like the framework parts of the team within the company. This company is so big. There's a lot of teams who like build the core parts of the frameworks. I tend to work with those teams to help them have their other developers be more productive. And that kind of is a way to fan out without having to do the coding yourself.
One from Conrad, your favorite method in .NET?
That's a hard one. Favorite method? Oh my gosh.
Probably to string, right?
Oh man, that's a good one. Favorite method. I need to go make one up. Favorite type, maybe? Method is like so granular. I'm thinking about types. Let's say I have a couple of favorite types, like pipelines, obviously. Channels, pipelines, I love. Um, I think those two things make like they're these types that let you express a whole bunch of patterns in a single type. So like I think you can model so many different patterns with those types directly that you don't have to like do a lot of stuff. So I'm gonna say channels and pipelines are my favorite types. The BCL.
Awesome. Question about surprises. What's becoming like?
After I don't have any surprises planned. We are discussing things for .NET 7, and there's a lot of stuff there. One of my personal pet peeves, things I am like trying to figure out how to push for, that's super hard. Like green threads. I'm super interested in Java's Loom and Go routines and fixing the async problem. So I've been looking at like researching all the things I can to figure out how others deal with it, to figure out what could work in .NET. So that's the thing that I have a thing for.
Awesome. What contributes most to performance improvements?
Interesting. For the improvements that you see that you get for free, I would say a lot of it is some of it is JIT. The JIT has improved a lot and can recognize more patterns that are in existing code already and that they get faster on every version. A lot of it is in the BCL libraries themselves. Like we just gutted a whole bunch of libraries and made them more efficient. Like for regular expressions, Stephen Toll basically spent like a month just making it extremely efficient and fast. And it's like things that we just didn't do for like, I don't know, 20 years that he just read a book and he was like, okay, I'm going to go optimize the crap out of like this engine now. And that keeps happening over and over. So things that you end up just using like string.index of like gets vectorized for free because we did a whole bunch of work in spans and that kind of accrues to overall thing. So it ends up being what we call peanut butter cost that kind of spread across the entire stack. It's hardly ever one big thing anymore. I think we haven't done all the big things yet. So in .NET 6, for example, we reduced memory of HTTPS connections by 4x. And it's like if you're seeing 4x improvement, it means that it hasn't we haven't looked properly yet, right? And there's a whole bunch of more stuff we could do too. So
cool.
A lot of those things.
A question related to obsolescence and making things obsolete.
Yeah, so we did have a big discussion, and I think the team now feels more comfortable marking things as obsolete. I think the challenge is, even if we do that, we need to come up with guidance. And like, there's all the Stack Overflow posts, and like, if you search for things online for how to do stuff, you will find ways to do them that are like 10 years old, right? So it's not just about obsoleting old types. It's about how do we actually get people looking and finding the right results, to find new tutorials, to find new ways of doing things. I think that is one that we haven't figured out yet, but we're trying to figure out how to tackle right as well.
Okay, so it's combined with education as well.
Yeah, exactly.
Okay, a question related to Bedrock.
Oh yeah, that's my baby. Yeah, I actually plan to put it on NuGet before the end of this year. So I want to get it to a state where like it could be a V1 and I put it on NuGet and then it can be used by people. I essentially like this is my way of getting a very efficient networking stack built on spans and memory and pipelines like in the ecosystem. I since doing Castro, I have an affinity for that kind of stuff. So it's my way of kind of like we need to get this thing out and get it be used. Like .NET is fine. It's a good project. I just think it's not .NET. It doesn't feel like .NET. It feels like Java and .NET. And this is why this feels more natural to me. I think at least that's why I did it in the first place.
Okay, question related to pipelines.
Yeah, it's funny. I saw a benchmark where someone was trying to benchmark pipelines over a file. So like the thing is, you won't see huge benefits unless you have high concurrency with async. The thing about async is that it adds overhead, right? So like you're doing more stuff. There's more queues, there's more threading, there's more completion, there's more dispatches to the thread pool. Like you're adding this overhead. So if you're doing a straight line test in benchmark.net for async IO, it's probably going to perform worse. You probably need like big chunks of memory, or you need to add some concurrency to make it actually go asynchronous. So I think so, but for this specific question, like I would say if you were doing it at scale in a web server, like async, obviously, like who wants to block trying to read files, right? And then the pin heap is tricky. Like to use it properly is very tricky. So maybe if you're super expert mode, use the pin heap. But for the most part, yeah, I would say use pool memory. Pin heap is kind of optional.
Okay, I need to select the last one because there are like 3 more or 4 more, but I think that will make the last one good. What's your favorite?
Ooh, this is a good one. Favorite. How about we do one that I use the most outside of C# maybe? TypeScript, JavaScript for front end, arbitrary front end stuff. I tried doing Python. I just don't like how it looks. But it's easy. I just don't love Python. I would say I do C# TypeScript. I've been playing with Go a lot. I wouldn't say I love it. So I would say like I play with C# JavaScript and Go. Those are kind of the 3 that I spend time on with.
Awesome. I think we have no more time for questions right now.
Okay.
So David, thank you for being with us, for making that happen. That was a really pure joy and pure pleasure. And I can tell that just by the number of questions being raised, that was an awesome presentation.
Awesome.
So thank you, folks. Thank you, David, for being with us, and take care. Bye.
Thanks a lot.